So we'll start with this topic, dielectrics and their polarization. So first we have to understand what is a dielectric. Now you already know what a conductor and what an insulator is. So let's read some theory about insulators first. Now, in insulator, the electron remain attached to the individual atom or molecule. However, these electrons can suffer small movement within the atom or molecule. So what does it mean? You already know that insulators are those in which the electrons, the outermost shell electrons, they cannot move free. They are not free electrons. They remain attached. Okay, the electrons remain attached to the individual atoms or molecule, but they can suffer a small movement. A small movement means, for example, let's say if you have an atom where positive and negative charges are, it's a polar atom. I hope you already know what a polar atom is. So polar atom, and you have, and positive and negative charges are like this. But if you keep this polar atom in a electric field, if you keep the polar atom in an electric field, the atom would then look like this. It will look like this, where the negative charge will flow towards the opposite of the electric field, and the positive will be like this. Okay, so they can suffer a small movement within the atom or molecule under the influence of an external electric field. The net effect of these microscopic movement give rise to some important electrical property to such material. So this is an electrical property. Why electrical property? Means every atom or molecule will not have similar behavior. Okay, they will have different behavior. That means in some molecules might be the negative positive charge will separate a lot of distance like this. Okay, positive negative charge will separate a lot. In some it will not separate a lot. So this is a kind of an important electrical property of the material, and this electrical property of the insulators are called dielectrics. So dielectric is effectively an insulator. Now, so dielectric is a substance which does not allow, dielectric is a substance which the does not allow the flow of charge, because dielectric is an insulator. What is a dielectric? It's an insulator. It does not allow flow of charge through it, but permits them to exert electrostatic force on one another through it. That means that dielectric insulator will not allow the flow of charge, but it will allow electric field to exist within itself. Insulator will allow electric field to exist within itself, but it will not allow the flow of charge. That means this positive cannot flow towards the negative, but this positive can exert an electric field to the negative. Okay. So a dielectric is essentially an insulator which can be polarized through a small localized displacement of its charge. Okay, very simple. Now, let us understand the behavior of insulator and conductor in an electric field. So let's say we have a conductor. This is our conductor. You already know that conductors will allow flow of charge. So when you put an external electric field onto the conductor, this is your external electric field. Let's give this electric field the value of E naught. Now, because of this external electric field, negative charge of this conductor is going to concentrate here. Negative charge of the conductor is going to concentrate here, and positive charge will concentrate here. Okay. And then the electric field will be like this. Because of this positive charge, the electric field again will come out. Mind it, this is a conductor. What is it? Conductor. Now, if the conductor is put in an electric field, this is how the displacement of the charge is going to happen. Okay, this is how the displacement of the charge is going to happen. Now, as you see, this displacement of charge will give rise to something called polarity or polarization. Why it is a polarization? Because now you can see that these two positive and negative charge are polarized. They are separated by a fixed distance. They're separated by the fixed distance. Now this is what's called polarization. So let's understand what is the polarization formal definition is. You see, polarization density, how much polarization has happened. The induced dipole moment. What is dipole moment? You have done dipole previously in the previous chapter. Dipole you have done, and dipole, you know, dipole always have a dipole moment. Here also you see that these negative and the positive charges are separated, and they are separated by a fixed distance. So whenever the two charges are separated by a fixed distance, you know that is a dipole condition, and it will also develop a dipole moment. You know this. So here, because of this positive negative charge, there is an induced dipole moment developed per unit volume of the dielectric. Okay, per unit volume of the dielectric in an external electric field. That is called the polarization density. Okay, very simple, and it is denoted by P. Polarization density denoted by P. Now, suppose the dielectric has a surface area of A. So this is our dielectric. It has a surface area of A and a thickness of D. So this is a thickness D. Acquires a surface charge density of plus minus sigma P. So surface charge density is this one. You see, because there is a charge accumulated here, so the charge over area will become your surface charge density. You will have a positive surface charge density here and negative charge surface charge density here. Your surface charge density would become QP over area. What is QP? QP is the charge acquired. This is the Q. This is Q negative, this is Q positive, and that's how you can calculate the surface charge density due to polarization. Now, if we calculate the dipole moment, okay, if we calculate the dipole moment, then what will be our expression for the dipole moment? You see, the dipole moment will be Q times D. You already done this in the dipole previous chapter, that the dipole moment of a dipole is the charge. Okay, dipole moment of the dipole is charge times the distance between the charge. In the previous chapter, the distance happens to be 2a or 2l, but here it is taken as D. D is the distance between the concentration of positive and negative charge. Now, so polarization, okay, polarization density P, polarization density will be the dipole moment of the dielectric. Just now we have understood dipole moment of the dielectric, that is Q times D, dipole moment of the dielectric Q times D, and the volume of the dielectric. Volume of the dielectric will become area into the distance A into D. These two DD will cancel, and eventually you will get Q by A, that is the density itself. So polarization density may be defined as the charge induced per unit surface area. Polarization density will be unit surface area. So now we will understand how the behavior of conductor and insulator in an electric field is. So again, this is our conductor. Let's say this is a conductor and this is our insulator. Now conductor, you already know that conductors allows the flows of charge. Insulator does not allow too much flow of charge. And if you put an electric field passing through the conductor and the same electric field passing through the insulator, okay, same electric field passing through the insulator, because conductor allows the flow of charge, so conductor may there will be a good polarization density. We have just understood what is polarization density. But in insulator, the polarization density is comparatively very less. You already know why, because the insulator does not allow the flow of charge too much, and that's why the polarization density will be less. The polarization density in the conductor will be very high. Now you can see this polarization density and the direction of the electric field due to this charge. So you see the direction of the electric field due to the polarization density will be exactly opposite. Let's call this electric field as EP, and the polarization density for the insulator also will exert an electric field in the opposite direction to the external electric field. That's also EP. So we have E naught, that is the external electric field, and we have EP, that is polar electric field due to the polarization. Now in the conductor, because the polarization is very intense or very high, so EP is almost equal to E naught. That is the electric field set up by the polarized charge is almost equal to the external electric field. But this is not the case in the inductor. In the inductor, EP is quite less than E naught. EP is very less than E naught, and that is also very evident why it is very less, because of the very less polarization of charge. So the net electric field inside the conductor, will become E naught minus EP. Why E naught minus EP? Very well, you can see that the E naught and EP are in opposite direction. So the net electric field will be E naught minus EP. And again, in the insulator also, the net electric field will be E naught minus EP. Now, because E naught is almost is equal to EP, that is why the net electric field in the case of conductor becomes 0. And the net electric field in the case of insulator is not 0. It's not 0. It is actually E naught minus EP only. So very well we can see that in the case of a conductor, the electric field, the net electric field inside is equal to 0, and that you already know from the Gauss's theorem also, you know that the net electric field inside the conductor is 0. But the net electric field inside the insulator is not 0. Okay, it is not 0, and it is E naught minus EP. Now, because of this electric field inside the insulator, the net electric field inside the insulator, which is not 0, E naught minus EP, we are now going to describe what is dielectric constant or relative permittivity. Now, dielectric constant and relative permittivity both are same thing, and that you have done this before in the previous chapter. You have done this dielectric constant, relative permittivity. Again, what will be the dielectric constant or relative permittivity is the resultant electric field in the dielectric will be E naught minus EP, that we have understood just now, and it will be in the direction of E naught. So the resultant electric field will be in the direction of the original. So where is the resultant electric field in the case of insulator? It is in this direction only. This is where the net electric field will be. Now, the dielectric constant or relative permittivity is this value. What is this? This is the electric field E naught divided by the electric field that exists inside the dielectric, E naught minus EP. And this is the value which is small k or epsilon r. Okay, small k or epsilon r. So this is what your dielectric constant or relative permittivity is. Our next topic is dielectric strength. Now every dielectric will have some strength. A strength means how much electric field it can tolerate. External electric field it can tolerate. Means when a dielectric is placed in a very high electric field, dielectric again it's an insulator which is placed in a very high electric, the outer electron may get detached from their parent atom, and the dielectric then behaves like a conductor. You see, dielectrics are insulator, and the insulator can then start behaving like a conductor. But this is only going to happen in a very high electric field condition. Don't assume any simple insulator is going to behave like a conductor in a very small potential difference or small electric field. No, that's not going to happen. You have to give very, very high electric field. And that is what the dielectric strength is. The maximum electric field that can exist in a dielectric without causing the breakdown of its insulating property is called the dielectric strength of a material. So every material, that is every dielectric, have a certain dielectric strength. Dielectric strength means the maximum value of electric field that it can tolerate, and beyond that the breakdown is going to happen, and then that dielectric will start becoming like a conductor. You see, vacuum vacuum has a dielectric constant of 1. Okay, and dielectric strength is almost infinite. That means vacuum does not becomes a conductor. Obviously vacuum means nothing, so there's no electron, no atom or molecule that can detach and start conducting. So vacuum does not become a conductor under any condition. But you see the air, you see air air has a dielectric strength, a dielectric constant and a dielectric strength. Water, paper, mica, all these, every known insulator have a dielectric strength. Dielectric strength means if you give more electric field beyond that, it will break down and it will start behaving like a conductor.